This video is a summary of the things that I went over on the section 9.1 video. And what I'm going to do is I'm just going to try to kind of quickly and briefly describe the ideas of hypothesis test. In that 9.1 video, I went into a lot of detail about how we think about and reason about all the tests. This is just a summary of everything so you can have it for you in a condensed place. So first, when we think about hypothesis tests, you really should categorize all of them into one of two categories for right now. The ones where the problem tells you what the standard deviation is, and the ones where the problem doesn't tell you what the standard deviation is. And that is either the standard deviation is coming from the whole population, or the standard deviation is coming from just the sample and not the whole population. But at any rate, as we do hypothesis tests, our test really falls into four distinct steps. So our first step is always to create the hypotheses for our test. And when we create our hypotheses for our test, we use H naught, and that's where we write mu is equal to, and we always have some number on the right-hand side, and this is your default assumption. So this is always the default. This is if there's nothing interesting in your problem, this is the number you would get. So we'll do a bunch of these, but you'll see that often you're comparing your sample to some population. If your sample's the same as the population, this is the number it should be. But if your sample's different, then you'll get some other result. Okay, so, and then we have an alternative hypothesis. And the alternative hypothesis is that mu, and then we use either greater than, less than, or not equal to, and we write the exact same number as what we had before. Whether we use greater than, less than, or not equal to depends on our study. So if you're doing a research study where you're trying to show that your sample has a greater average than the population, then you're going to use greater than. Similarly for not, less than, or equal to. This is usually what you want to show. So usually when you're doing a research study, this is what you really want. So if you're a professor and you're trying to show your students are doing better on the test, this is the default score on the test. What you're really hoping is that your students are scoring greater than whatever that score is on the test. So the second one is usually what you want. Once you've created your hypotheses, the next step is always to create your test statistic. And your test statistic is really going to depend on whether you know or don't know what sigma is. So what we did in section 9.1 was our test statistic, where we had x bar minus mu divided by sigma over the square root of n. And so we just put all of these numbers into our calculator and we come up with our result. Okay. So this mu is whatever number you're using up here. So if this number is 50, then you're going to put 50 down here for mu. This number is going to be found in your study. For the textbook, usually the number will be given to you, or you'll be given some collection of numbers that you find the average and put there. Okay. Again, sigma is given to you, and n is just how many people are in your sample. Once you've created your test statistic, the next step is to find your p-value. And for a p-value, I always draw this picture, and then once you have your picture, you come here and we shade in one of the sides. This is a greater than example. So if you're doing greater than z, then you shade in the right-hand side. If it's a less than, you'll have a picture where we shade the left, and if it's not equal, you'll shade both sides. And so this part right here is what we're going to call our p-value. If we're dealing with a z, so if we're starting with a z problem, then that means we're going to use normal CDF to solve our problem, because normal CDF is how we calculate areas under a normal distribution. And so use normal CDF with mu equal to 0 and sigma equal to 1. So keep those as a standard normal distribution, because z means it's standard. Finally, once we have our conclusion, we really compare everything to whatever our alpha value is. So we have two possibilities for our p-value. Either our p-value is smaller than our alpha value, and alpha is going to be given to you. So remember, alpha is what we call the level of significance. This is the point at which we've decided if we're smaller than that point, then we're going to reject our hypothesis. And if we're bigger than that point, then we're going to fail to reject our hypothesis. So If the answer from here is smaller than alpha, then we reject our null hypothesis. And if P is greater than whatever that alpha is, we fail to reject our null hypothesis. Now, what's important here, right, is that we're either rejecting or failing to rejecting. We never prove our null hypothesis, so we never accept our null hypothesis. Our null hypothesis is the default, so it's probably true without evidence to show otherwise, but our test is only capable of either saying the null hypothesis is false or we're unsure. The null hypothesis could be true or false, and we're unclear. Okay, so this is what it looks like if we know what sigma is. If sigma is unknown, most of these remain pretty similar. So our null hypothesis, we set up our hypotheses the exact same way. So we do our hypotheses the exact same whether we know what sigma is or not. The big difference is our test statistic. So instead of using z equals to x bar minus mu over sigma over square root of n, you use t. And instead of having a sigma, we have an s over the square root of n. So really our problem looks the same. Notice the formulas are basically the same. The only difference is here we're using s because we don't know what sigma is. Once again, what's the difference between s and sigma? S is the standard deviation for your sample. Sigma is the standard deviation for the entire population. To find our p-value, we do basically the same thing. We still have our same picture. Now we're using a t, and we're shading in some side. Again, I'm shading in the greater than side. If the hypothesis was different, we would shade in a different side. But this is our p-value. But the only difference is because it's a t and not a z, now instead of using normal CDF, we're going to use t-CDF. And then our degrees of freedom is going to equal whatever n minus 1 is. So if we had 50 items in our sample, we're going to use 49 for these degrees of freedom. It's just 1 minus whatever that sample is. And finally, our conclusions are the exact same. So once we have this p-value, we make the exact same conclusion. We draw our conclusions in the same way. Okay, well, hopefully that small sample kind of, this little summary helps organize things. I was hoping this might be something that you come back to if, for example, you get a problem or two down the road, or you come back in a day or two like, man, I don't remember what was happening on these tests. You can look in your notes, or maybe this little video might help you just clear some things up, organize things in a nice, clear way for you. All right, what we're going to do now is I'm going to go through all the rest of the problems in the book. I'm going to go through, or in the notes, I'm going to go through 9.5, 9.6, 9.7, and 9.8. So I'm going to make each of these their own separate video. So what you need to do is you need to get out your pencil and calculator, try each of those problems on your own, and then after you've tried it, check the video to make sure you're doing it correct and make sure you're following all the things that I anticipate you doing. Finally, I'll have one final video on how to use our calculator, and that's going to be your favorite part of the video, or your favorite part of the section. But as always, we don't want our calculator to be our crutch. We want to use our calculator only after we understand the process and what's happening to it. So go try those problems, come back and watch the rest of the videos.